ماذا لو أن الكفاءات الجزائرية من كافة أنحاء العالم تجتمع معاً؟ ماذا لو أن هذه الأدمغة بمختلف تخصصاتها تتكاثف لتطوير التعليم والبحث العلمي للنهوض بالجزائر في مختلف المجالات؟ هل تعتقد أن هذا مستحيل؟ أبداً، فالحلم يتحول إلى حقيقة من خلال الشبكة العالمية للعلماء الجزائريين إيناس. رغم أن إيناس هي مؤسسة غير ربحية وتعتمد فقط على تبرعات الأفراد، إلا أنها استطاعت أن تبني جسورا من التعاون وتبادل الخبرات بين أبناء وطننا الحبيب من الداخل ومن مختلف بلدان العالم، ساعية لصقل المهارات واحتواء المواهب وتبادل الخبرات وإيصال التجارب النافعة لخدمة الوطن.
All right, good afternoon, ladies and gentlemen, and thank you very much for joining us in another webinar in our webinar series Advanced in Geoenergies and Renewables of the International Network of Algerian Scientists. My name is Mohamed Amrouche. I am the project leader and the initiator of this webinar series. And the objective is to try to spread science and try to share the expertise on the field of the geoenergies and renewables for each month, and by inviting world-renowned experts. For this month, we are very honored and happy to have Dr. Steve Cuddy to do the presentations. Good afternoon, Dr. Steve Cuddy. Thank you very much for accepting our invitation.
Thanks for the invite.
Thank you. Thank you very much. So I will briefly introduce our keynote speaker today. Dr. Steve Cuddy is a retired petrophysicist, having worked with Schlumberger, BP, and Baker Hughes. He holds a PhD in petrophysics at Aberdeen University. He holds also a bachelor in physics and bachelor in astrophysics and philosophy. He is the inventor of the fractal foil function that describes the distribution of fluids in the reservoir model. He writes AI softwares and has 45 years industry experience in petrophysics. In recognition of outstanding service of the SPWLA, Steve has awarded the Distinguished Service Award in 2018, and today he's going to introduce a very original topic entitled Why Fractals Make Reservoir Modeling Really Easy. Dr. Steve Cuddy, please, the floor is yours. Can you please share the slides, please?
Right. Can you see my presentation?
Did you share your screen? Please share full screen. We can see the presentation.
Share, yes. Okay.
Oh, yeah, I think we got it. So we got it. Yes. Right, please go on full screen mode, and we can start the presentation. Yes. Hide this one and goes on. Yes, we can see it very clearly. Please just hide the small bar. Yes, please, the floor is yours. Thank you very much.
Right.
Please go ahead.
The technology. Well, thank you everybody for coming along to my presentation, Why Fractals Make Reservoir Modeling Really Easy. This is derived from an SPWLA Distinguished Speaker presentation that I was giving last year. And it's all about fractals. Now, fractals are not only very pretty, but they're very useful, as I will explain today. So this is an outline of my presentation. I will remind you what fractals are and the fact that we see fractals everywhere. And how do we verify something is fractal? I'm going to show you two very different ways of proving something is fractal. I'm going to remind you why we need a reservoir model and why fractals make reservoir modeling really easy. So this is the diagram you've often seen of fractals. And as you zoom in closer and closer, the fractals go on forever. That's amazing. But we actually see them in nature as well. We see fractals on a very small scale. If you've seen snowflakes, like on the left, these are fractal patterns. As you're getting closer and closer, you see a repeating pattern. You find fractals everywhere. Let's put a pointer on. Also in nature, and this is a cauliflower, and you can see a repeating pattern here as well. So this is on the small scale. Now we also see fractals on the big scale. On the left, we've got the Himalayas, and this is a chain of mountains, as you know, across Asia. But as you zoom in, from looking in space towards the Himalaya, you see these patterns of ridges. And as you get closer and closer, the shape of the ridges repeat themselves. On the right, I've got some river channels. I took this photograph myself a couple of years ago when I was asked to give this presentation in Basra in Iraq. And as you get closer and closer, you see that these shapes are the same all the way down. So we see fractals on the big scale. Now we also see fractals on the really big scale. Now what can't be bigger than the cosmic microwave background? This is tens of billions of light years across. And this is what we see. It's a cosmic microwave background. And this is taken from a book by Professor Brian Cox. This is a picture here. And what he notices, as you zoom in on this background, you see patterns. And the patterns repeat themselves. Now, these patterns are very important because these patterns give rise to galactic superclusters. And inside those superclusters, there are galaxies and so on. And each of these shapes is the same. So the universe is fractal from all the way up to all the way down. So to remind you, what are fractals? A fractal is a never-ending pattern. Closer you get, the pattern repeats. As you zoom out, you see the pattern again. It's an infinitely complex pattern that looks the same on every scale. And what's important for us in reservoir modeling is that it's created by a simple repeating process. And if you can unlock that process, then you can use it in reservoir modeling. This is an example by B.W. Mandelbrot, the inventor of who coined the phrase fractals. Other names for fractals is self-similarity, as you see the same thing over and over again, and also scale invariance, which is very important in petrophysics and reservoir modeling. So fractals are objects where the parts are similar to the whole except for scale. Let us take this example, this cartoon of a tree. This is what a tree looks like from a distance. You get the main trunk, and then you get main branches and smaller branches all the way down to twigs. Now, what you do notice is that as you get closer to the tree, the major branches are the same pattern as the overall tree. And as you get down to the smaller and smaller branches, you get to the twigs, and it has the same pattern. You may ask, why is it fractal? There's a good reason why it's fractal. This tree, big and beautiful it is defined by its DNA. And there's a simple repeating instruction in the DNA which says grow a bit, then branch, grow a bit more and branch. And from that very simple instruction, you get a very beautiful and complex tree. Now, how do we verify that something is fractal? Now, I'm going to show you two different ways. Let's take this example here from which I took from the internet. We're going to look at the coastline of Great Britain, as shown here. And we want to measure the length of the coastline around Great Britain, as we do here with the ruler. So we need a ruler to measure the distance, such that if we have a very coarse, long ruler, this will be the distance around Britain, shown in purple. So this will give us a perimeter of 9. Now, if we use a smaller ruler, as shown in red, then the ruler would get into the estuaries and the little shapes around Great Britain, and the length, the coastline, N, would be even greater. Similarly, if we want to look at the actual bays and estuaries inside Great Britain, we could take a smaller ruler, as shown here in orange, and we would get a longer coastline. So however small we make the ruler, we get a longer and longer coastline. But what happens if we plot this? So I'm going to plot the change of the ruler length, which is R here, against the length of the coastline on log scales. As the ruler shrinks, the measured coastline increases. And we get this, if it is fractal, then we get a straight line. So these are the 4 rulers shown here in different colors: purple, red, orange, and yellow. And these are the dots on this log plot. And what we notice that these points fall on a straight line, a linear line, and this proves that the coastline is fractal. And the gradient of the line is what we call the fractal dimension. Now we're going to look at some reservoirs in a little while. So let's remind ourselves why we need a reservoir model. A reservoir model is very important, as shown here, as a cartoon of different colors like Lego bricks. And the reds could be different porosities, the yellows could be different facies, but we've got a reservoir model. The purpose of the reservoir model is to be able to calculate the hydrocarbon in place, and also to know where the best placement for wells are. This is a static model, and it can be enhanced to be a dynamic model. Now, the reservoir model requires us to know where the fluid contacts are. It needs to know what the net reservoir cutoff is, and it needs a water saturation versus height function. This is needed to be able to initialize the reservoir model. Now, we've got a very limited amount of data from the reservoir model from where we've drilled the wells, as shown here by these 5 wells. So there's a very limited amount of data, core data and electrical log data from these well locations. And you can imagine this is a very small percentage of the whole reservoir. So to be able to derive a good reservoir model needs to be able to understand the SW height function and where these contacts are. So let me remind you, the SW height function is used to initialize the 3D reservoir model. It tells us how the water saturation varies as a function of height above the free water level. And I will go over these definitions in a moment. What it actually tells us, it tells us how the formation porosity throughout the model is divided between hydrocarbon, oil or gas, and water. And it tells us what we know as the shape of the transition zone, as shown here. So you've got the free water level and water saturation, and normally, as you rise above the free water level, the water saturation reduces and you get more hydrocarbon. But that's not always the case. This is a very simple schematic. So this is where the reservoir model needs an SW height function to be able to initialize itself. Now, a good SW height function requires 3 independent sources of fluid distribution data to be consistent: formation pressure data, electrical log data, and core data. The function must account for varying permeability and fluid contacts. It should be convincing, and it should be easy to apply. Before I show you the function we're using today, I want to run over these definitions, which are simpler than you think and are often misunderstood. There's four definitions I'm going to run over very quickly. The first of these is the bulk volume of water, or BVW. If we take a unit piece of rock containing the matrix, we have porosity, and the porosity is divided into hydrocarbon and water. The BVW, which is very important in this presentation, is defined as the percentage of water in a unit volume of rock. It is simply the product of porosity and water saturation. So it's the percentage of water in a unit volume of rock. Now, we do not measure water saturation. What we measure is BVW. When we measure electrical tool in a borehole, what we're measuring is the conductivity of the bulk volume of water. which depends upon the salinity. We do not measure SW directly. In fact, it's a distraction. When we do core analysis, you get core analysis reports. It's all tabulated as with water saturations. But core analysis does not measure water saturation. It measures BVW. It always measures the amount of water dispelled from the rock under different pressures. And if you want SW, you have to divide by porosity, which is another measurement. So electrical logs and core data do not measure SW directly. And this presentation is going to stay in BVW space, the bulk volume of water. A very important definition for the reservoir model is the free water level. The free water level is an horizontal surface of zero capillary pressure. If you drill the well where you're located now, a very wide borehole, eventually you get to a point where water would be coming to the borehole and you would get a free water level. This is where the fluids separate in a wide borehole. It is also the intersection of the formation pressures in a well. So you've got a gradient from the water leg and a gradient from the hydrocarbon. And where they intersect, these two straight lines, we've got the free water level. It's important, the free water level, for the SDRI function because it's the base from where it starts. So what the free water level is a very simple definition. It's an horizontal surface of zero capillary pressure. Now let's compare that with the hydrocarbon water contact. The hydrocarbon water contact is a height where the pore entry pressure is sufficient to allow hydrocarbon to start invading the formation pores. So this hydrocarbon water contact is a varying shape, and it depends upon the local porosity and permeability, as I will show you in some slides later. So this is a variable height compared to the free water level, which is a plane and which is what we'll use for the model. The last definition I want to tell you about before we look at the function is the irreducible water saturation, SWIRR. It's defined as the lowest water saturation that can be achieved in a core plug. But let's try to understand what we mean by the lowest water saturation in a core plug. The water saturation in a core plug is achieved by flowing hydrocarbon to the sample or spinning the sample in a centrifuge to dispel the water. So the SW actually depends upon the drive pressure or the centrifugal speed. So the water saturation depends upon the height above the free water level. A minimum SWIR does not exist. Your reservoir engineer may ask for an irreducible water saturation. There is no such thing. If your reservoir continues and continues, then you get lower and lower water saturations. The transition zone extends indefinitely from the free water level to infinity. Now I want to tell you about water. Water is very important in this presentation. It's even more important than the hydrocarbon. Now we all know that water is H2O, 2 atoms of hydrogen and 1 atom of water. But what you probably didn't realize, it has this particular shape, like a boomerang, where the hydrogen, which is predominantly positive, and the negative oxygen on the other side. So it has this distinct shape, and this causes the molecules to be strongly attracted to each other, water to water, and also to the surface of reservoir rocks. So you've got positive and negative together, and this electrostatic force is 10 to the power 36 times greater than the gravitational force. So the water is very powerful. So what are the forces in the reservoir? These are very simple. There are 2. The water is in the reservoir first. When the hydrocarbon migrate into the trap, the buoyancy force exerted by the lighter oil or gas will push the water downwards, down towards the free water level. However, not all the water is displaced. some of it is held by these massive capillary forces within the pores. Now, narrower pores have smaller pore throats and a larger surface area and will hold onto the water the strongest. So you've probably seen this, a little capillary tube when you were at school. A capillary tube held in water will cause the water to rise in the tube. This is caused by preferential wetting of the walls, and it gives rise to this particular shape. What you probably didn't realize is that the shape on the outside is even greater than on the inside. That is simply because the surface area is greater on the outside of the tube than on the inside. So this is what you often see. You see three different capillaries, a large, a medium, and a small. Now, what you notice is the smallest throat drive up the most water. But what we're interested in is the other way around. The smallest pores hold on to the most water because it's got the larger surface area for the volume. Consequently, hydrocarbon requires more pressure to enter the small pores. I won't go too much into the mathematics. It's in the paper, which I will give you a reference to later. But the parameters are very well understood, relating capillary pressure to interfacial tension and the size of the capillaries. Now, the other force in the reservoir is gravity. This is a lot weaker than the capillary force, but it's important. The force of gravity on a column of water is determined by the difference between the densities of the fluids, and it is called the buoyancy pressure. And it is given by this very simple relationship here. Now, what are these two forces going to do in the reservoir? You've got one force is the capillary force, which is holding up the water. And then the other force is the force of gravity pulling the water down. Now, the hydrocarbon is the mobile phase and is only allowed to enter any leftover space that the reservoir pores do not want for the water. The water was there first and determines what stays. Consequently, a given part of the pore space within the reservoir will contain both oil and water. And we understand the percentage of that is the water saturation. So this is what you normally see. Now, the capillary bound water comprises of a continuous column of water within the oil lake with an hydrostatic pressure gradient as shown here. So you got the pressure against height, the free water level, and you have an hydrostatic water gradient below the free water level. And this gradient continues linearly above that, but only in the water phase. Now, the formation pressure tester, which measures the pressures, actually can only measure the mobile phase, which is the oil or gas gradient, which is a lower gradient as seen there. Now, we know that the intersection of the hydrocarbon gradient with the hydrostatic water gradient is the free water level. So it's important to realize the formation pressure tester only sees the mobile phase, even though there are two phases actually in the formation. A continuous water phase with the capillary bound water and a continuous hydrocarbon phase. The water phase is capillary bound and the hydrocarbon is free to move. Now, the buoyancy pressure, which is the difference between the oil and water phases, increases with height above the free water level, as shown here. The difference gets greater. As the buoyancy pressure increases with height above the free water level, the oil phase will displace more water from the increasingly smaller pore volumes, pore spaces. So the hydrocarbon can get into the smaller spaces. Therefore, the water saturation will tend to decrease with the height above the free water level. It will tend to, but I will show you this is not always the case. Now, reservoir rocks are fractal. There have been many studies done, and this is an example of a study on reservoir rocks. We have imaged the rocks using a scanning electron microscope, and this is a picture we have taken here. Okay, and we can dye the rock such that it represents the porosity. So we could put a blue dye into rocks, and that would represent the porosities. So all we would need to do to calculate the porosity of this piece of rock would be to count the number of pixels, which are blue, which is the porosity, and divide that by the overall size. But what you see is that maybe if we get smaller pixels, like the rulers around the coastline of Britain, we would get more porosity. So you would think that we get an infinite amount of porosity if we're not careful. So as we zoom in upon our rock, we get more and more porosity. But if we plot the pixel size searching for these little blue porosities, which are porosity, against the overall, we get a straight line. And this proves it is fractal. And I'll show you a different, separate way of proving it is fractal. This is an example from a Brea sandstone from the North Sea. And there are many of these in the literature. So the reservoir rocks are fractal. So why is this important? It becomes very useful in reservoir modeling because many complex objects can be described by fractals. And fractals are a mathematical simple way of describing complexity, like in the tree and in the rivers, in the mountains. Now, so it's very useful in hydrocarbon reservoirs, as I explained. The mathematics are in this paper here, if you wanted to follow it through. But basically, the very simple equation at the basis of this is a fractal formula which describes the porosity is related, how it's related to the rock capillaries. So we've got this very simple equation, which is an established fractal formula for reservoir rocks. And if we manipulate that using our capillary pressure theory, we derive this function here. Remind you, BVW, the bulk volume of water, is proportional to the height above the free water level with two different constants. So this is a very simple equation which is going to describe a reservoir model. So let me look at some real data. This is water saturation against height above the free water level from the North Sea gas fields, right? We plot water saturation on the x-axis against height above the free water level here in feet. And we have colored the z-axis by porosity. So the ice porosities, which represent dune sands, are shown in red, and these are off to the left, lower water saturations, right? Then we've got fluvial sandstones in blue in the middle, and off to the right we've got the sandy sapphire, the poorer sandstone, still reservoir, but to the right. So what we notice is the higher porosities are to the left. You get a asymptotic curve here through the red points. And then as you get to lower porosities, you move to the right. But not only do you move to the right, but also there is an offset such that in low porosity formation, the formation could be fully water saturation for hundreds of feet above the free water level, shown here. Now we need to describe this arrangement in our reservoir model. But we get a very typical shotgun pattern. So how can we describe this? Well, historically, they've broken down this presentation into different porosity bands, where we've got high porosities here and low porosities to the right. And so we derive a different curve for each porosity band. And you can see there are some problems here. These curves will cross over. And to be able to derive this line here, you must drill a well in a poor part of the field deliberately so that you can fit the curves. And it's very difficult to fit this curve unless you know what the offset is. This is an actual plot from a field development plan in the UK. So, in conclusion, you need sufficient data for each of the porosity bands to fit the curves, and they're unconvincing because they're going to cross each other. And you don't know what the pore entry pressure is really to be able to define the endpoints. So we need a better way. So let's use our fractal function. So this is our water saturation against height, this shotgun pattern. We want to bring some sense to this. Now what we're going to do is we're going to change the x-axis, the water saturation, with BVW, the bulk volume of water. We're just going to change one click and we're going to change it. And you can do this yourself on your own data. And this is what we get. Identical number of points are plotted. Nothing has been filtered out. And what you see is that the water saturation moves to BVW. All the data collapse to a single curve. And this is a single curve here. But the important thing is the porosity is mixed up. So it's independent of porosity. So the BVW was derived from the fractal formula. And you can prove that it is independent of porosity, fascist type, and permeability by using that powerful petrophysical technique called the cross plot. So you make a cross plot of BVW against height, and the z-axis, you put your zone number, your permeability, you color it by porosity, and so on. And if the data is all mixed up, it is independent of that parameter. So to remind you, this function, the fractal function, is BVW is equal to H to B. H is the height above the free water level. BVW is the bulk volume of water, the percentage of water in a unit volume of rock. That's what we actually measure in core analysis and in log analysis. We don't measure water saturation. And we've got two constants. So this equation is derived from the fractal nature of the reservoir rocks, and it is based on BVW rather than water saturation. And if we can show it is independent of fascist type, porosity, and permeability. Such that if you get this kind of plot, that is also proving that your reservoir is fractal. So this function is independent of fascist type, zone number, porosity, and permeability. At this stage, we have just got two parameters which are completely describing your reservoir. Remember that reservoir you want to understand with a minimum number of well locations. So here's our equation. BVW is equal to H to B. Now, I want you to cast your minds back to school and what happens when you take the logarithm of both sides, or you plot this function on log scales. So when this function, exponential function, is turned to log scales, you get this equation here. The equation turns from an exponential into a linear equation, as shown here. Now, I'm showing you here several different fields which are completely different, and we're plotting BVW against capillary pressure. Capillary pressure is equivalent to the height above the free water level. And what you notice is that each of these lines is linear, as you would expect. So our function, we need to derive from the core data A and B from this data. To calculate a straight line, you only need two valid core points. So all these core points, which cost many hundreds of thousands of dollars to collect, really we only needed two good ones to be able to derive our function. And not only that, we've got two parameters which derive the curve. You notice that the gradients are all the same. The gradients are the same, and the gradients is actually turns out to be 0.42. The answer was 42. So we've got one parameter which is completely describing a complete field. The gradient is scale invariant. That means that if you change from capillary pressure to height, from feet to meters, you get the same gradient. Now let me show you the use of that SWI function. There was an SWI height challenge by the London Petrophysicist Society a number of years ago. One of the companies could not fit an SDI function to this data set. And what they did, they challenged the petrophysicists in the UK to see if they could give a good function. So let us see why this is a very difficult data set. In the left-hand column, we've got the water saturation, and it doesn't decrease with height as you'd expect. The porosities vary a lot. The permeability varies from millidarcies to darcies. And what we want to do, we want to be able to describe this water saturation here. This water saturation is derived by the Arch equation from the resistivity log, but we need to program it into our reservoir model. So we need an SDI function. So there's a shootout between several functions by comparing the function against the water saturation from the resistivity log. And this is the result. We've got the fractal function shown in red, which is based on BVW, the buffer water, and that is compared to the resistivity-derived water saturation shown in black. So there's a very good match between the function and the resistivity log in all different lithotypes. Even though there's a massive variation in permeability, you can see that the water saturation, which is shown in white here, is increasing steadily with depth. So this is very useful for the reservoir model because permeability is not required to predict the water saturation. And it's defined by only two parameters, A and B, or perhaps only one parameter. This match is so good in this difficult well, you would want to ask, do we always require resistivity logs? What do I mean by that? Well, perhaps in a field, we derived our BVW function based on the first wells, and then a later well, we just a development well, we have the resistivity log has failed. Would we want to go back into that well and run the resistivity log again if the model could predict water saturation as well as this? Something to think about. So what does the fractal function tell us about the reservoir? So we've got the BVW shown in blue in the unit volume of rock. If we consider a certain horizon in the field, in the reservoir model, on the left-hand side, we've got good porosity, say 20 porosity units. And on the right, we've got 10 porosity units. Remember, the water was there first. And the water, with its massive capillary force, holds onto the rock. And the hydrocarbon can only enter what is left over. At 20 porosity units, on the left-hand side, we've got a oil saturation of 60. On the right, the same height in the reservoir, which are much lower porosity, the oil saturation is only 20. But what we notice, the BVW is the same. The BVW is because the BVW is independent of porosity. And this is actually telling us what our net reservoir cutoff is. In this case, is 9 porosity units. So can we believe the fractal function? Does the fractal function predict the correct water saturation? Let us compare water saturation derived from resistivity log by the Arch equation from core analysis and from this function. In this case, we've got very accurate core water saturations. The Dean and Star shown in the blue dots. The well was drilled with oil-based mud and doped to identify any contamination. And these are good core water saturations. Now, the resistivity log is shown in black, and the fractal function is shown in red. The resistivity log predicted water saturation is very pessimistic. It is giving us high water saturations. And why is this? In this case, the resistivity log is affected by the conductive shale beds and the thin bed effects. By looking at this central track, the fractal function is closer to the good core water saturations, where the resistivity log is pessimistic. So the resistivity water saturation is too high in thin beds. So that's why we believe the fractal function by comparing with core. Now this function, will not only give you a good reservoir model, but it will actually give you two models. It's a differential reservoir model, as I will explain here. We've got the fractal function on the right here, shown in the red for hydrocarbon and blue for water. And we've got the resistivity log. The resistivity log is very useful because this is telling us what the saturations were yesterday when you logged the well, where the fractal function is telling us what the distribution of hydrocarbon and water was after the initial fill of the reservoir. So the resistivity log represents the current oil in place, and the fractal function represents the initial oil in place. And as you see at the top of this interval here, we have a difference between the fractal function and resistivity log. And this is suggesting that this interval has been swept. And not only has it been swept, this is telling us what the irreducible oil saturations are. But further down in the reservoir, surprisingly, we've got the water saturation from the resistivity log is identical to the fractal function, and this is telling us that this is a bypass zone which needs to be searched after. The resistivity log is incorrect in thin beds, close to bed boundaries, and where the conductive shales, because of the excess conductivity of the shales. The fractal function, in comparison, ignores thin beds, bed boundaries, and shales. So we can use this function to pick our free water level. We need to know this horizontal plane for our reservoir model. So this is an actual example from the North Sea, two wells that didn't intersect the free water level. When you plot BVW rather than water saturation against depth, the data falls onto a single curve, and then you can actually predict the free water level, as shown in this case here. And the free water level is one of the inputs you need for the reservoir model. Now, the hydrocarbon to water contact is less important, but if the reservoir engineer insists upon it, you can easily calculate it. This is the varying surface of hydrocarbon in the reservoir due to the change of pore perm throughout. And if you divide your BVW function by porosity, you just get SW. And such that you get, these are the curves which drop out. So SW for different porosities is shown here. And this will tell us that this formation is fully water saturated, 200 feet above the free water level, if the localized porosity there was 5 porosity units. This function also can give you uncertainty, and this is very important for the reservoir model. You can actually do partial differentiation of the fractal function to derive upside and downside functions. There's more information about this in the paper. So rather than just giving the reservoir model an average, most likely function for the fields, you can give the modeler upside and downside functions. And these upside and downside functions include the uncertainty in the porosity, resistivity logs, and Archie parameters. So this is very useful, that then you can run it through the reservoir model and it can give you upside and downside volumes of hydrocarbon, which the client is very interested to know. So you give not only a most likely model, but an upside and a downside model of the function. So I'd like to show you this very interesting comparison now at the end. I'm looking at 11 different fields, which was the data was acquired over many years. And these fields were selected because they're very different, as shown by these different colors. We've got different fluids in the reservoirs, gas, oil, or condensate. And we have different geological ages and very different pore perm. But generally, they all fall on the same pore-perm trend. So we've got very poor reservoirs and very good reservoirs. Now, what did the BVW functions, the fractal functions, tell us about these reservoirs? So we're actually comparing the transition zones. So we've got BVW against height. If it was for a constant porosity, say we're comparing 20 porosity units in each, well, you could change this to water saturation. Now, if you wanted a good reservoir, what would you select? You would say, I want a reservoir which has got very high porosity, because the porosity is where the hydrocarbon is held. What else would you want? You say, I want a field with very good permeability, because permeability is the conduits of flow from the hydrocarbon to the wellbore. But also we would say we would like an SWI function, which is on the left here. So the lowest water saturations are on the left-hand side. So this is the kind of function we would like. And these colors here are correspond to the previous slides. And you will get a copy of these slides after this presentation. So the thing which is controlling this is just the A parameter, because they've all got the same gradient. The A parameter defines the pore geometry. Now, let's have a look at this plot. We're plotting two different data sets. We're plotting our fractal function from the resistivity logs on the left, and on the right, we're plotting the BV function from the core analysis. So in the core analysis, we've taken lots and lots of measurements. So that's why there are more lines. Again, the colors refer to those fields. And what you notice is that the gradients from the core analysis is the same as from the logs. So this is amazing. The core plugs are very small plugs, maybe a cubic inch, where the logs are measuring the function from the top of the reservoir to the free water level. And why are they the same? Why do we get the same function? Because the reservoir is fractal. You can send away your little core analysis and the piece, and the function you get from that can be used in the complete reservoir. Because it's the same, you can use these plots to do a quality control. So you can quality control the core analysis against the logs by seeing whether the gradients are the same. And because the gradients are the same from the logs and from the reservoir capillaries, this confirms the fractal distribution of the reservoir capillaries. So in summary, reservoirs are fractal in nature. This can be shown by analyzing the log, the porosities, and making a plot of porosity against pixel size, or you can make a BVW plot to show that it is fractal. So it can be verified by a simple cross plot, a very powerful tool for the petrophysicists. The fractal equation is very simple, and it leads to a very convincing SWI function. And this gives a distribution of hydrocarbon and water accurately throughout the reservoir model. It also gives us our net reservoir cutoff. The net reservoir is a rock which is capable of holding hydrocarbon. It gives us a free water level, the hydrocarbon water contacts if you need them for the reservoir model. It is independent of porosity permeability. You don't need a geologist. It's a simple function of height. And it can be derived from electrical logs or the core data by a very simple linear regression of a log-log plot. So it's independent of rock characteristics. You can prove that by making a cross plot, and this makes reservoir modeling very easy. So this is the key conclusion. Forget about water saturation on the left and think BVW. The BVW is related to the fractal nature of the rocks and gives a very simple function, which is the same in a small scale as a large scale. So I'm happy to take any questions now or by email. I just want to say that I provide free consultancy. Right.
Thank you very much, Steve. Thank you very much for the very original and interesting presentation you presented. Really an original idea here using fractals for petrophysical analysis. You started by showing fractals are everywhere, and then you covered some fundamentals on petrophysics, and then finally showed some very interesting results and conclusions. So I'd like to remind our audience that now we are moving to the Q&A session, and you can ask your questions to Dr. Steve Cuddy on the comment sections. I can see that we have a few questions already on the chat, so we start picking some questions. First questions from YouTube is saying, Steve, how will you differentiate between mobile and Connect SW if only BVW is used?
Well, in this model, it is very simple. You have a free water level, and all the fluids above the free water level, the hydrocarbon is a mobile phase. Below the free water level, the water is a mobile phase, and this is the reason why we always get a straight line when we make a pressure plot. Originally, when the formation tester came out, they thought that the curves would be actually curved because the water saturation was varying with depth, and they were very surprised that the lines are straight. And this is because the formation tester is only responding to the mobile phase. And above the free water level, you've got capillary bound water, right? And so the mobile phase is the hydrocarbon. So you see the hydrocarbon above the free water level, and below the free water level, you see the mobile water. If this was not the case, you would not get the distribution over geological time between hydrocarbon and water.
Thank you. Thank you very much for your response, for your answer. So I would like to remind our audience that we are in the Q&A session now, and you just type your questions or comments on the comment section during this live so that we can answer them. So I pick another question from Facebook now. Thank you very much for the lecture. Where can we get the equations used on the fractal function estimation? They seems to be quite straightforward to use, and I want to try them in some of my data set. So I don't know if the data are, there's the equations can be used. Where can we get the equations? Probably, I just remind our audience that Dr. Steve Cuddy shared with us the PDF slides. So we are trying to discuss with our communication team how we can share them publicly, right? So maybe, answering this question. Sorry, go ahead, Doctor.
Yes, we'll provide you with the slides, so you don't have to make copious notes. And also the SPWL paper describes the derivation of the function. Now, I'm happy to give consultancy for free on this, because a lot of reservoir engineers overcomplicate it. They try and make it better. But in actual fact, if you make a very simple plot of SW against height, and then you change the x-axis from SW to BVW, you can see how powerful it is. So, and then the power is that in log space, it's a straight line. So you just plot the net data above the free water level, put a line through it, and that's your BVW function. And the actual details of that are in the paper, which we'll make it available to you all.
Thank you very much. We will also add the reference to the paper later after this live. We will pick another questions from LinkedIn this time. So I remind our audience that we are now in the Q&A session, and you can type your questions and comments and in the comment sections, and we will pick a few of them. So from LinkedIn, Thomas Jerome is saying, hi, you say that BVW is independent of porosity and permeability, okay? But yet we have different A and B constant in different reservoirs. So what is causing these different values? So Mother Rock's characteristics, hydrocarbon characteristics.
Well, you say, well, if BVW is independent of porosity and permeability, why do we have a different function in different fields? That's a very good question. The answer to this is very simple. It's because you've got one field. Even Leverett J function assumes that you've got the whole reservoir is represented by a single capillary. So the BV function is one value for that field, and it depends upon the density of the hydrocarbon, the salinity of the water, and the average pore geometry. Now, if you had two fields which were next to each other, they would have different BVW functions. But if you were able to put them in communication with each other, they would reduce to a single function, right? And that's what we're working on. We're making it simpler. We went from two parameters to one parameter, and we're trying to understand that one parameter now. And that's why we see different BVW functions in every field. The field may have 1,000 wells, but it'd be just one function.
Thank you. Thank you very much for the answer, Dr. Steve Cuddy. So, yes, I myself have another question. So I would like to know if you tried this method on different reservoir types. I would like to highlight the difference, if there is any difference between carbonate reservoirs, let's say, and silicoclastic reservoirs. We know there is a lot of anisotropy in carbonate. So is this method applicable? And can we see any fractal patterns in carbonate as well?
You can use this function in carbonates and in clastics. And in fact, carbonates are, as you say, more complex, and you get a more convincing function there, because the amount of variation in fractures and in porosities mean that you cannot understand water saturation in carbonates. But the BVW function simplifies it. Yes. So it works in carbonates and in clastics. All you need to do is make that plot. You've spent lots of money deriving the data from the subsurface. Yes. You've spent a lot of money getting your best minds to analyze the data. All you need to do is one click to move from SW to BVW to say, it is fractal, because it is all condensed, collapsed onto one line. So yes, it works. It works everywhere. Yes.
Thank you very much. Yeah, maybe similar question. Is it working similarly for oil and gas, for example, or what type of gas or fluid? Viscosity of the liquid we are dealing with? Have you tried any different type of fluids reservoirs?
It's independent of the salinity. It's independent of the hydrocarbon density. You can prove that by putting as your z-axis on your plots. It doesn't matter if it's gas or oil. It works very well. Yeah.
Thank you. Thank you very much, Dr. Steve Cuddy. I think we are reaching almost 1 hour webinar here, so I'd like to close this Q&A section. We picked some of the questions. I would like to reiterate our acknowledgement to thank Dr. Steve Cuddy for accepting to be our keynote speaker this month. And please stay tuned with our international network of Algerian scientists. We are keep having monthly webinars. Hopefully in December, we are going to invite one expert discussing hydrogen. So it might be a very, very interesting topic. So with that said, I would like to thank our audience that watching us live now, and we'd like to thank Dr. Steve Cuddy for the very, very interesting and insightful lecture. Maybe a final words, Dr. Steve Cuddy, before closing this webinar.
Yeah, thanks for inviting me. Just to say, I am retired, but I love to receive BVW plots, and I will give free consultancy on it, because it's just looking at plots is very easy for me. So please send me your plots.
Thank you very much. Thank you very much. I think everybody have your email now, so feel free to reach Dr. Steve Cuddy and discuss BVW plots. So again, thank you very much for watching us, and thank you, Dr. Steve Cuddy, for the very, very interesting webinar. So with that said, thank you very much.